Hello everyone. Today we are going on an imaginary journey to a place more than 400 million miles away from Earth, to the largest planet in our solar system, Jupiter. Jupiter is no ordinary planet. It is massive enough to fit more than 1,300 Earths inside it, and its gravity is more than twice as strong as all the other planets combined. For decades, astronomers could only marvel at the beautiful, multicolored clouds on the outside of this giant, but no one could say for certain what lay beneath those cloud layers, thousands of miles deep at the very center. Everyone assumed there would be a solid, rocky mass at the core. It seemed logical. After all, a planet this massive must have had a firm foundation to form. But now, all our assumptions have been overturned. We have discovered that Jupiter's core is not what we were taught in science textbooks. It is in a state that is entirely strange and exciting. In today's program, let's travel into the interior of Jupiter and uncover these secrets together. Recent state-of-the-art tests have revealed something no one expected. Jupiter's core is not a solid, a liquid, or a gas. It is something much stranger. What does this impact our understanding of this planet and the gas giants of the universe? How did Jupiter's core actually form? And how significant is this for what we know about our solar system? For a long time, astronomers were divided between two main theories of how Jupiter formed. The first, gravitational collapse theory, suggests that Jupiter formed directly from the solar system's gas clouds without a solid core. According to this view, gravity caused a massive cloud of hydrogen and helium to collapse all at once, creating a giant planet that never quite became a star. This theory explains well why Jupiter is so massive and primarily composed of gas. However, it faced one problem. It couldn't explain how a dense and distinct internal structure developed, something suspected due to the planet's intense gravitational field. Alongside this assumption, another theory emerged and gained more support over time: the core accretion model. This theory posits that Jupiter started like the rocky planets, as a solid core formed from the collisions of rock and ice fragments in the early solar system. As this core grew, its gravity increased, allowing it to pull in vast amounts of hydrogen and helium from its surroundings. Thus, a massive layer of gas surrounded a dense core. For decades, the view that Jupiter had a solid core at its center dominated scientific literature and astronomy books. It was estimated that this core could be 10 to 20 times the mass of Earth, composed of iron, silicates, and carbon compounds. It was believed to be separated from the surrounding layer of liquid metallic hydrogen by a sharp boundary, which made calculating internal structure and magnetic field generation simpler. But one fact bothered scientists. These theories were based on models, not direct observations. No one had ever seen Jupiter's core. It was estimated only through its mass, size, and gravitational pull on other objects. Therefore, there was always the possibility that these assumptions were wrong. Then, spacecraft began sending back the data astronomers had been longing for. To everyone's surprise, the data didn't just prove the old assumptions wrong, it revealed that the core was composed of a very strange substance: the mystery of liquid metallic hydrogen. Spacecraft that first approached Jupiter, like Voyager in 1979, collected valuable data about its atmosphere, magnetic field, and size. But the turning point came with the Galileo spacecraft, launched by NASA in 1989. Galileo was the first craft to enter Jupiter's orbit, sending back detailed information about the atmosphere, radiation, and composition for over 7 years. The most interesting findings came from indirect measurements of the internal structure. One of the most shocking discoveries was that a very strange substance might exist in the deepest parts of Jupiter: liquid metallic hydrogen. On Earth, under normal conditions, hydrogen is a gas, but under the extreme pressures tens of thousands of miles below Jupiter's surface, its atoms are so tightly compressed that electrons can flow freely, just like in metals. In this state, hydrogen can conduct electricity and generate magnetic fields. This is crucial for understanding Jupiter's magnetism. According to Galileo's measurements, a large portion of Jupiter's interior could be composed of this strange substance. This created a major inconsistency. If Jupiter's core was completely composed of liquid metallic hydrogen, how could it have formed in the first place? According to the core accretion theory, Jupiter needed a solid core to start pulling in gases. A liquid core, by nature, wouldn't provide an effective starting point to pull and aggregate gases. This problem led to a fundamental question. If there was no solid core, how did Jupiter pull in all that gas in its early stages to become what it is today? Scientific opinions diverged. Some argued a solid core still existed, but was hidden under dense layers of metallic hydrogen, making it impossible to detect accurately. Then, as the puzzle grew more complex, a mission arrived that changed everything: Juno. When NASA's Juno spacecraft reached Jupiter in July 2016, the goal was clear: to study the planet's atmosphere, magnetic field, and especially its interior more precisely than ever before. Unlike previous craft, Juno didn't just orbit the planet, it traveled in an elliptical path over the poles, approaching as close as 2,600 miles, 4,184 kilometers, above Jupiter's cloud tops. From that vantage point, Juno obtained unprecedentedly precise gravity data. One of the primary instruments on Juno is the Doppler measurement system. This system tracks tiny changes in the frequency of radio waves sent between Earth and the spacecraft. As Juno approaches a dense area of Jupiter, its speed changes due to local gravity, causing a Doppler shift. By carefully studying these changes, scientists can map the distribution of mass inside the planet. What they discovered was stunning. If Jupiter had a precise, solid core, its gravitational field would be uniform and predictable. But Juno found the opposite. Jupiter's gravity was not uniform, it was lumpy. This meant that the mass of Jupiter's core was not concentrated in one spot. These findings gave rise to a new concept, the fuzzy core, or dilute core. Instead of being a solid ball of rock, ice, and metal, Jupiter's core is a vast region where these heavy elements are gradually mixing with the surrounding liquid metallic hydrogen. Scientists are still investigating whether this resulted from a collision between planets or if it formed this way from the beginning. Jupiter isn't the only one like this. In 2021, using a technique called ring seismology to study the rings of Saturn, it was confirmed that Saturn also has a fuzzy core, extending up to 60% of the planet's radius, just like Jupiter. This indicates that for gas giants, this structure is the norm rather than the exception. These discoveries require us to reconsider the internal structures of thousands of exoplanets outside our solar system. It has forced a fundamental rethink of how mass is distributed in planets, how thermal energy moves, and how magnetic fields are generated. What started as a simple question, what is at the center of Jupiter, has opened a door to understanding how planets across the universe are born. The universe remains more mysterious than we ever imagined. I hope you enjoyed today's presentation on the secrets of Jupiter. What other space mysteries would you like to know about? Perhaps its giant storms or its moons? You can leave a comment. Thank you all.